Hey guys, today we're going to be doing max and min problems, and I also have a surprise. We got the pen back. I just bought a new one, but yeah, he's going to carry us a long way. He's brand new, got a full cartridge. Anyway, this is, just so you know, this is my least favorite part of the course. But I think this kind of thing, max and min problems, are 3 videos, and we're just going to try and steamroll through them in the next couple of days, because then we get to do double integrals and triple integrals for the next 1, 2, 3, 4, 5, 6 lessons, which is going to be super fun. So okay, well, let's see. Now, if you remember in Calc 1, when you have a point where f prime of c is equal to 0, right, that just means the slope is 0. There's no slope at this point, and so c is a critical point. And then this point is either a max or a min. And you could also identify whether it is a max or a min by either plugging values, or you could use the second derivative, right? So if f double prime of c is greater than 0, then that tells us that so this is how this is how slope is changing. Slope is increasing as you move along the positive x direction. So for slope to be increasing, picture this like a parabola. So slope is negative, 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 0, positive, 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 positive. So if it's going from negative to 0 to positive, then slope is becoming negative, or slope is becoming positive as you move along the x-axis, and that means the plot is concave up, concave up. Okay. And conversely, if f double prime of c is less than 0, then you have the opposite. He's concave down. He's sad. Okay, yeah, so of course, in multivariable calc, you can still use the derivatives to find max and mins, but you would have to use the partial derivatives. I think I kind of went through a problem on a past exam that kind of dealt with this, but I didn't quite realize that we would be going over this exact approach in this video, but it's there if you want to. It's in the, yeah, I think the previous video, one of the last 2 videos for sure. So okay, yeah, so you could still find derivatives in z. If you have z equals a function of x and y, you can still use derivatives, but you have to use partial derivatives because you have to check in both the x and y directions. So you find these critical points by finding that fx equals 0, right? The partial derivative of z with respect to x, and fy has to also be equal to 0, right? You can't have one be 0 and the other one not be 0 for this part of the course. Yeah, I don't think you really go into stuff where, I don't remember at least, having to deal with one of these being 0 and one of these not being 0. So yeah. Okay, so to identify these points, there's 3 identifications, like 3 categories this could fall under. Well, you have a min, right? That would be like a paraboloid, where you have something like this, right? And this is like your min. You have a max, just invert that, max. And then you have a saddle point. What's a saddle point? Here, I got you. It's this Pringle-shaped thing. You see these in hyperbolic paraboloids and stuff. But yeah, it's this Pringle shape. And the reason this is its own characterization is because you realize that as you do it in different directions, it's different, right? So if you're going down this direction, he's concave up. But as you're going from here, he's concave down. So you can't say he's a min or a max. He's kind of in the middle, right? Now this isn't strictly an x or y direction, but you still can't really classify it as a distinct min or max. And obviously with these examples, you can see that it doesn't just have to be the x and y direction. Any direction you approach it in kind of has the same result, where it's like the maximum here, right? Any direction you approach this point from, not just x and y, you always get to this minimum. But here, it differs. From this direction, it's concave up. This direction, it's concave down, right? Min, max, min, max. So you can't really say it's a min or a max. So yeah, that's a saddle point. Okay, and how we identify these is we use this thing called the discriminant. This is what it is. D equals the second derivative with respect to x times the second derivative with respect to y minus fxy, so the partial derivative with respect to x, and then take the derivative of that with respect to y, and then you square him. Okay, and this guy comes from this thing called a Hessian matrix. I'm not quite sure where it comes from or why it's relevant to this, like, to finding maxes and mins, but it's basically a square matrix. So it's like a matrix, it's like n columns, and then n rows and n columns, and it's made up of all second order partial derivatives of a multivariable function. So yeah. Okay. Now what happens? Like, what do you do with this? So there's a bunch of things that could happen. If you manage to plug in all your values and you get d is 0, then the test is inconclusive. And honestly, I'm not sure if there are other ways to classify that point, because this is the only test they give you in this class. And if you plug it in, get an inconclusive test, then you literally don't have anything else to do. That's going to be one of your answers. It's going to say, oh, it's inconclusive. If d is less than 0, then the point is automatically going to be a saddle point. And then you have two cases for d being greater than 0. Okay, so if d is greater than 0 and fxx slash fyy, these are, if this is greater than 0, then these have to share a sign. And you can kind of see that in the math. If you look at this equation, this term is always negative, right? Because you're squaring something, this is going to be positive, and then you're subtracting a positive. So if these guys don't share a sign, then you're going to have a negative times a positive, and you're going to have a negative minus a negative, and you're going to get a negative d, which gives you a saddle. Okay, so these two have to share a sign. So if fxx is positive, fyy is positive. If fyy is positive, fxx is negative. Okay, so if d is greater than 0, and these guys are both greater than 0, then you could think of it like this, where it's going to be a concave up, right? So it's going to be a min. You could use the approach of, oh, if the acceleration, or god damn it, if the second derivative is getting higher as you move in a direction, then it's like, oh, it's negative here, negative, oh, it's getting smaller, it's 0 now, and now it's increasing, right? Then that's a min. Now, if both of them are less than 0, then that's a max. Okay, and you could use the same approach if it helps you remember. But really, it's just a matter of memorization if you don't want to think about it that way. Okay, so let's do like a quick example. So if you have z equals 10 minus x squared minus 5y squared, you're gonna first do partial z partial x, and that's gonna give you minus 2x, and then partial z partial y, and that's gonna give you minus 10y. So then you get that for this guy, you have x equals 0, and then for this guy, you have y equals 0. So, so note this, for this next example, that's going to be pretty hard. Obviously these derivatives can get way uglier, and you can have x's and y's in one derivative. So the way I'm going to motivate thinking about this right now is you want to find so critical points are points that will make both of these equations 0. So I could say that for this guy, this equation number 1, for equation 1 to be 0, then x can be 0 and y can be a constant, any constant, right? Because this isn't dependent on y. Y can be anything for all I care, but as long as x is 0, this is 0 as well. Same thing with here. Y could be 0, x can be that is not anything. X can be literally anything, some kind of constant. And you get the same thing. This is always going to be, what do you call it? This is always going to be 0. But these constants are not interchangeable. So what I'm trying to say is, if you get a point that satisfies the partial derivative with respect to x equals 0 for one of the equations, it better satisfy the other partial derivative equaling 0 as well. So 0 comma c here makes this guy 0, but it does not make this guy 0. So this is not a critical point. Okay? What makes both of them 0 is just the origin. So that's our only critical point over here. And that makes sense, right? This is an upside down paraboloid. So that, okay, well, I kind of spoiled it, but you expect to find a max, right? Because he's gonna have that shape. Okay, so fxx, you could see that that's negative 2. fyy is negative 10. And then fxy is 0. So this equals 20. Okay, so d is greater than 0. And then fxx and fyy are both less than 0. So I always have to run through the same example again, where this means the every time this means the goddamn, this means the second derivative is getting smaller as you go through time. So here he's really positive, so happy. Then he gets zeroed, and then he's negative. So this guy is concave down, so that's a max, which is what we expected, right? Because this is a upside down paraboloid. So yeah, another quick tip. Yeah, so I kind of touched on this earlier when I said that these guys have to share signs. But if they don't share signs, you automatically have a saddle. You will not have a min or a max, and you won't have an inconclusive. And the reason you won't have any of those is if these guys are opposites. So, hold on. So this guy's positive. This guy's negative. This is always going to be a negative value. This is a negative number. So you're going to have negative number or 0. But regardless, you're doing a negative minus a negative. So this equals a negative number. So you're not going to get 0 out of this either. And you're not going to get a positive number out of this either. So it can only ever be a saddle point if the signs of fxx and fyy are opposites. So yeah. Okay, next example. This is where the point I made earlier is really gonna matter. The point I made about points not being shared between the partial derivatives. So, let me find it. Okay, so let's take this example. Yeah, okay, I really don't feel like writing on the left side of the page. I'm gonna just, okay. Xy times e to the negative x squared minus y squared. Okay, so of course, first step, you want to take fx. So this is just, what do you call it? This is kind of a product rule and a chain rule. So you have, if you say f is x and then g is y times e to the negative x squared minus y squared, then you take the f prime times g is going to be y e to the negative x squared minus y squared, and then you're going to add it to x times the derivative of this guy, which is going to be, let's see, it's going to be y times e to the negative x squared minus y squared times negative 2x. Was that right? Let's see. That's going to be minus 2x squared. Yeah, okay. Yeah, so you have this guy, and then you're going to multiply him by y times e to the negative x squared minus y squared times negative 2x. And then you can factor out this y equals y e to the negative, that entire term. So you're going to have y times e to the negative x squared minus y squared times 1 minus 2x squared, right? And you want this guy to be equal to 0. So you have two things that can happen to make this guy 0. Y can equal 0, or this guy can be 0. So 1 equals 2x squared. 1 over 2 equals x squared. So plus or minus 1 over root 2 equals x. So or x equals plus or minus 1 over root 2, right? Okay, so now let's do the derivative in the y direction. So if you do this, it's pretty symmetrical. You're just gonna swap the x's and the y's. You're gonna get x e to the negative x squared minus y squared times negative 2y squared plus 1. So it's basically the same thing where you get that either x is 0 or y equals plus or minus 1 over root 2. Okay? And what is it? Now you have to be extra careful about deciding your pairs. So remember, we said that 0 comma plus or minus 1 over root 2 doesn't mean it will satisfy this guy being 0. Okay? So one thing that does make both of these guys 0 is 0, 0. Okay? Oh, yeah, you also have 1 over root 2, 1 over root 2. Right? And then the negatives of that, negative 1 over root 2, comma negative 1 over root 2, and then the mixed sign versions of those as well. So lastly, you have this guy. Okay. And it's really tempting, but you will not have a point that looks like this or a point that looks like this. And I'm going to emphasize this because this is really important to know for these kinds of problems. This or tells you everything. Either this or that. You can have both, but not always. This is a trap they probably like to play around with a lot. So yeah, you can't have this because if you plugged this guy into this equation, you're not going to get 0. Same thing here. If you plug this guy into this equation, you're not going to get 0. So it doesn't solve the problem we want to fix. Okay, so now you basically take all these points and you plug them into, well, actually, using, let's just take fxx and fyy because we're not quite sure yet. But yeah, so if we take fxx, okay, so I just took the derivative. It's not completely simplified, but here, I'll just simplify it for you. So this is just y e to the negative x squared minus y squared times negative 6x plus 4x cubed. You can factor out 2x from here. So this just equals 2xy times e to the negative x squared minus y squared times, if you factor out a 2x, you would have 2x squared in here, 2x squared minus 3. 2x squared minus 3. Okay, so this is fxx, and then fyy, just by symmetry, is this guy, 2y squared minus 3, and then fxy is, let's see. Let's just take, this is fx, so let's just take the derivative of that guy with respect to y. Derivative of this guy with respect to y. So if we take this guy as f and this guy as g, it would just be e to the negative x squared minus y squared times negative 2x, or negative 2y, times 1 minus 2x squared. Right? And then can we simplify this at all? Let's see. You would have negative 2y minus, or plus 4x squared y. Oh, wait, hold on. I'm being silly. You have a whole product rule here. This guy's just a constant. Yeah, so the product rule is going to be e minus x squared minus y squared plus y times e to the negative x squared minus y squared times negative 2y times 1 minus 2x squared. All of this times that guy. So if you simplify this, you will get e to the negative x squared minus y squared times, what is that, 1 minus 2y, 1 minus 2y squared, because you're multiplying this guy and this guy, and then you have this times 1 minus 2x squared. Okay, so that's fxy. Okay, so if you plug in all these points, I mean, is this really worth it? Do we really want to go through all of 5 of these points? Well, if you have, we'll just do 0, 0, because this is taking up some time. But yeah, if we do 0, 0, you're gonna get e to the 0 times 1 times 1 is 1. So that's fxy. Fyy is gonna be 0. Fxy equals 0 as well. So this tells you that you're gonna have 0 times 0 minus 1 squared, negative 1, which is a saddle. Okay, and you know, we just for funsies we can plot this out. Just to see what this plot looks like, actually, because it's kind of complex. I actually don't know what this looks like. Oh, fun. Nope, no, not there. That's really interesting little plane. Okay. So okay. Interesting. Yeah, so you could see the here we'll just do one of the points, one of the 1 over roots. there it is. Okay. So this is the plot. It's kind of like a plane, but he's got some bumps. So there's the saddle point. You see that it's pretty obvious if you look at it from here. If you look at it from here, it's a min. If you look at it from under, it's a max. So it's a saddle. And then this is positive 1 over root 2 comma positive 1 over root 2. That's a maximum. You can see the minimums right there. There's the other maximum. So pretty neat little plot. I actually didn't know that's what it would look like. But now we can just do it on the empty page that I left earlier. But now I have 3 practice problems left, from past exams. So this problem tells you to find the point x comma y. The point at which x comma y at which f has a local minimum. So f of x comma y, and they tell you it's this 1/3 y cubed plus x squared plus 4xy minus 2x minus 13y plus 7. Okay, so if you take fx and fy, let's see, fx, it's going to be 2x plus 4y minus 2. Okay, and then take one more derivative, you're going to get 2. Fy, that's going to be y squared plus 4x minus 13. One more derivative, you're going to get 2y. Okay? And now fxy is 0. Okay? So, and you want a local minimum. So what does that mean? Local min, that's when d is greater than 0. But that also means that fxx and fyy have to be, if we want a min, it's like that. Slope is getting more positive, so it's greater than 0. Okay? So if you multiply these two together, you have 4y is greater than 0. So that means y cannot be negative. So basically y must be greater than 0 for this to happen. So if we look at our option choices, this is what they give you. They tell you none of the, they tell you 1 comma negative 13, 3 comma negative 1, 1 comma negative 3, negative 17 comma 9, or none. Now immediately, because we know y has to be greater than 0, you could eliminate this guy, and this guy. So it's either negative 17 comma 9 or none of them. It can still be none of them. The way that would happen is if this guy doesn't satisfy our equations up here. If we plug this point into these derivatives and we don't get 0 for both of them, then the answer is none. So let's try that. So if we plug this point into fx, which you guys can see up here, you're going to get negative 34 plus 36 minus 2. That looks like it'll be 0. And then if you plug them in the other one, you have 81 minus 17 times 4 is 68 minus 13. Yeah, that looks like it's 0. So it's this point. It's got to be this point. Yep, let's go. Okay. This one, according to the second derivative test, the critical points of this function are, okay, so they give you f of x comma y equals x squared times y cubed minus y plus y squared. And we can just take the derivatives. Let's see, if we take the derivative with respect to x, this guy's just a constant. You have 2x times y cubed minus y equals 0. And fy is x squared times 3y squared minus 1 plus 2y. So from this first guy, we get that either x is 0, y is 1, or y is, what's that, y cubed equals y. That means y squared equals 1. So y is plus or minus 1. So y can also be negative 1. Okay, so now we can, so now if we look at the second one, if we try solving that for 0, 2, it gets pretty ugly. So what we could do is we can plug these points in and solve for values of x or y that satisfy it being 0. So if we plug in x as 0, then you get 2y equals 0, so then y is 0. And we automatically have a pair. That's a pair. Okay, if we plug in y as 1, then you have x squared times 3 minus 1, that's 2, plus 2 equals 0. So you get 2x squared plus 2 equals 0. You can quickly realize that this doesn't have any real solutions, right? You can't get some negative number out of this in order to get that to be 0. So this doesn't have any real solutions. If you plugged in y equals negative 1, well, you're going to get, let's see, 3y squared. That's 2x squared minus 2 equals 0. So x squared equals 1. So x equals plus minus 1. Okay, and that's our second pair. So you get 1 comma negative 1 or negative 1 comma negative 1. So these are all of our pairs. Let's 0, 0, 1, negative 1, negative 1. Okay. So we had these points, 0, 0, 1, negative 1, and negative 1, negative 1. Okay. Now we have to classify these guys. So if we look at our derivatives again, oops. So 2x times y cubed minus y. So for x we had 2x times y cubed minus y, and then in the y we had x squared times 3y squared minus 1 plus 2y. Okay, so fxx is just going to be, this times a constant, so it's just going to be 2 times y cubed minus y. And then fyy is going to be x squared times 6y plus 2. Okay, and then fxy, so you could take the derivative of this guy with respect to y. That's going to be 2x. Thank you. 3y squared minus 1, right? Okay. Okay, let's plug in 0, 0. So for 0, 0, this is going to be 0. This is going to be 2. And then this guy, he's going to be 0. So you have 0, so it's inconclusive. So 1 point is undetermined. If you look at the options, that eliminates, here, I'll put it a bit closer, that eliminates this guy, not this guy, not this guy, but this guy as well. So do we have 2 saddle points and an inconclusive point, or a min and a max? Okay, so let's just plug in one of these guys. So if you plug in one of those guys, you're going to have 2 times -1 plus 1, so that's 0. That doesn't give me a lot of hope, because you're going to have 0 minus, if you plug in, let's see, that's going to be 2 times, oh, that's a negative number, but that's going to be a saddle point. Yeah, you're going to have 0 minus some kind of number. You can get negative k, that's a negative number. D is less than 0, so saddle. So that will be option C, 2 saddles and 1 undetermined point. Yep. Okay, last problem. So they tell you, consider the function f of x comma y equals xy to the 4th minus x minus half x squared, and it wants you to find, it says among its critical points this function has, and it wants you to say an absolute min, an absolute max, blah, blah, blah. Okay, so you want to take this dude's derivative. Fx is going to be y to the 4th minus 1 minus x. Then fy, you will have 4xy cubed, and that's it. So x can be 0, or y can be 0. Okay, so if x is 0, we're going to look at fx. So if x is 0, then this is what's going to happen. You're going to have y to the 4th minus 1 equals 0. So y to the 4th equals 1, which tells us that y is plus or minus 1. Okay? So that's our pair. Now if y is 0, okay, then what's going to happen? You're going to have minus 1 minus x equals 0. So then x is -1. So this is our second pair. So yeah, let's write out our pairs. So we have 0, 1, we have 0, -1, and then we have -1, 0. Okay. So now if we plug them in, we can take second derivatives, correct? So if you take fxx, let's define these down here. Okay, so fxx is going to be -1. fyy is going to be 12xy squared. And then fxy is going to be 4y cubed. Okay. So now let's start plugging these points in. So what I'm noticing from the start is that, so the formula is this. Oops, not that. It's fyy. Okay. If you plug in anything that has 0, this entire thing is going to be 0, right? Because fyy is just a product of 12x and y. And if one of these guys is 0, then the whole thing is going to go to 0, and if this guy goes to 0, you multiply it by this guy, which is also 0. So you just have negative 4, or well, you have this, negative 4y cubed squared, which is negative 16y to the 6th. Okay, so it's all completely dependent on the y value. So if y is 0, which is in this guy right here, you're going to have an inconclusive point, because d is 0. Okay. Also, because this is an even power, it doesn't matter if y is positive 1 or negative 1. This is always going to be negative 16. So if you have negative 16, if you have a negative d value, then that's a saddle point. And you're going to have 2 of them, right? Because no matter what you plug in, you're going to get negative 16. So this is kind of a weird question because it says, okay, so it's not this. We have saddle points. It's not, doesn't have 4, doesn't have minimums. It does have 2 saddle points. It doesn't have a maximum. This is the right answer, but it doesn't include the fact that it has an inconclusive point, but yeah. Okay, I hope today's video was not too bad. Tomorrow it's going to be pretty lame, just like this kind of, except with boundaries. But yeah, okay. As always, let me know if you guys have any feedback. I hope my videos are okay. Thank you.